in assigning probabilities, we have two ways. We can assign probabilities based on empirical evidence or on logical deduction. And we have two rules that we follow by convention when I assign probabilities to the outcomes in a sample space. So if I have an experiment with outcomes, let's say E1, E2, E3, and we're not exactly sure how many might be there, so let's say there are n of them. And to each I assign a probability. Let's call that probability P1 for E1. P2 is the probability we assign to E2, etc., etc., etc. Pn is the probability we assign to En. Our rules are as follows. By convention, we assign a probability between 0 and 1 to each outcome. And this reflects the proportion of times we would expect this outcome to occur over many trials of the experiment. And it should also reflect the relative frequency we observe over many trials of the experiment by the law of large numbers. We have one other rule that we follow, and that is that the sum of these probabilities equals 1. So when I add the probabilities of all of the outcomes in the sample space, I should get 1. And these are our two basic rules for assigning probabilities. And this last one can be interpreted as saying that the probability that something happens is equal to 1, or we're certain that something will happen. Let's take an example. Suppose my experiment is to flip a coin, a fair coin, and the possible outcomes are heads and tails. And we've seen before, both by logic and empirical evidence, if I were to flip that coin 1,000 times, I would assign a probability of 1/2 to each of those outcomes. This table is called a probability distribution, and it gives me a complete list of the possible outcomes for the experiment and their probabilities. I can also represent this probability distribution graphically. For each outcome, I draw a rectangle above the outcome, and I keep the bases of the rectangle of equal width, and the height of the rectangle is the probability of the outcome. So these bases are equal. And the height here for each of these rectangles is 1/2. And because I'm keeping the bases equal, the area devoted to each outcome is proportional to the probability of the outcome. So this type of graph, this type of representation of the probabilities respects the area principle.